welcome to the next lesson of the Healdsburg Hacker Club. Today we're going to put circuits down for a minute and we're going to talk about the concept of bases, counting systems. And the reason why is because you and I are used to counting in decimal, where 1 through 10 and then 11 and 12 and so forth. However, computers can't count that high, or they can, but they can't count in decimal, in the decimal system. They can count in a different system called binary or base 2. So we kind of need to understand what's going on with that, because that's how the processor works on the inside. So let's just do a quick example of how decimal works. This is base 10, so I'm using Excel to keep things nice and orderly here. So as you know, you can start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in our system, we actually have a different looking character for each number between 0 and 9. And the total number of characters we have here is 10, 0 through 9, so that's why we call it base 10. What that means is if we want to count any higher than 9, we don't have a single character that means 10. So we actually have to start using multiple digits, as we know, and we put 10 in like that. And so what we've done is we've reset. The right character is now back at starting at 0 again, and we've incremented the left character, which you can kind of imagine an invisible 0 next to the left of each number. And we don't show it because why bother? If it's 0, who cares? But we now need to show it because we've changed it from a 0 to a 1. And then of course we proceed from there. And we keep counting with this 1 in front until we run out of numbers on the left again, or characters on, on the right again. And now we increment the 1 to become 2. And so we all know how this works, of course. However, let's make up a new system. Let's call it base 3. All right. So in this case, you'd have 3 characters: 0, 1, 2. Now, if you want to count any higher than 2 in our new base 3 system, we have to do the same thing now that we had to do down over here when we went to 2 digits here. Well, now we need to go to 2 digits here because we only have 3 characters in our system of base 3 to work with. So we do the same thing. We increment the 1 to the left, and then we reset to 0 on the right. So it looks like this. So what we know, the number 10 in base 10 looks like to us, in base 3 is actually the same thing as the number 3 of what we know. So it's like 3 apples. This is the same way as saying 3 apples in base 3, which is kind of weird, isn't it? That looks like 10, but in base 3, that's different. So let's keep going. We can go like this. All right, so we're at 12, and we have the same problem we had here, which is that we can't count any higher than 2 on the same, we don't have any characters higher than 2, so we need to reset this 2 back to 0 and increment the 1 to the left of it. So it's like 20. You guys see how this works? 21, 22, 23. Oops, not 23. There is, and I missed 22. So again, we have to increment and go back to 30. And let's say we go all the way down and skip a whole bunch, and we get all the way to. Oh, I made a mistake. I made a big mistake. I'm sorry. After 22, we ran out of. We filled up these two digit places or placeholders with 2. We have nowhere to go. We need to turn this to a 0. We need to turn this to a 0, and then add and continue using a new place to the left. So it looks like that. So I fell in my own little trap there. 22, 100, and then we are free to go back to 0, 101, 102, and then continue on like that. We increment 1, 1, 2. I got to be careful here. 1, 2, 0, 1, 2, 1. Is that right? Let's see. 10, 11, 12, 20, 11, 100, 1, 2, 1, 2. Yeah, I'm doing all right. I'm about to fill up though. So again, we need the first 2 places from the right are filled up, so we need to increment over. We jump up to 200, and then at some point we'll get to 222. I don't know where it's going to be. And again, as we filled up here, we need to go add a digit. We're filled up with all the highest characters here, and nowhere else to go. We need to add a new digit. Looks like that. So, and then you can go all the way up to 2,222. The next one after that would be 1 or 10, what looks like 10,000. So we keep adding. So what's interesting I want to point out is look how inefficient this base 3 is, because to show the number 15 and what we're used to thinking of 15 in base 3, it takes 3 places. whereas with our decimal system it only takes 2 places or 2 digits. So the smaller the base is, the more, the fewer characters you have to work with is another way of saying that. The more inefficient, the more digits it takes to actually represent a number. Okay, so base 2, which is what binary is, I'll put binary here at the top as a little note. This is what the computer's thinking. So we can do 0 and we can do 1, and that's great. However, we're done. That's 2 characters, and that's what base 2 means. We're done. We cannot count any higher than 1 without having to move over to the left. So here comes the next number in binary. And all right, 10. That's what it looks like, 10, but really that's the binary version of 2. I'm going to hide base 3 here since it might be confusing. So we're going to compare binary only to base 10 now. So I'm going to go to 11. That's easy to do. Now I've run out of, I can't increment any other number. I've run out of digits, so I need to go to 100. Make a new place, and then 101, 110, 111. I've run out again, so I have to go at another place. Now I can work with these zeros for a while until they get filled up. Right? And then, oop, my heater turned on. Oh well, we can ignore that. Or did I count that right? Yeah, I did. 1101. In fact, there's a neat little function in Excel I'll see if I can use here. Bind to, actually it would be the other way around. Decimal to bin, and I click on this number, and it does it for me. You can see that now. I can drag that all the way down, and it copies that. And why don't I just make these all look the same? So you can see the number 30 is really easy to do in decimal, but over here we have to use 1, 2, 3, 4, 5 digits. In fact, let's do 31, and you can see all 5 are filled up. So if I go to 32, then I have to move over to 6 digits just to show the number 32. So base 2 is a very inefficient way to show numbers. You have to use so many digits to keep up with decimal. But that's how it works, and that's how computers think. So there we go. I want to introduce another base that we might run into called hex, hexadecimal really. And hex means 16. This is going to be base 16. So how does that work? Well, this works as before, 0, 1, 2, 2, 3, 4, 5, 6, 7, 8. So we borrow the same characters that we have in decimal. However, we say base 16. That means there's 16 characters to work with. That means that these 10 digits here are we have more of those, more than 10. We should have more than 10 to work with. So we're going to borrow some other characters from the alphabet to continue on. So the letter A means 10, B, C, D, E, F. Okay, let me just put them all together there. So there's our base 16 system. It goes all the way up to 15 decimal before we run out of room. We're at F, we can't go any higher, so then we do the same thing as before. We increment the left one, which is 0, becomes a 1, and we go back to 10. And we go all the way, let's say 11, 12, 13, so forth, all the way up to 19 at some point, and then we continue on past 19 with 1A because we can go further than 9. Remember, 9 is no longer the limit for one character in a hex system. 1B, 1C, 1D, 1E, 1F. Now we need to increment the next one over 20. And if you keep going down, let's say we count all the way up to 95. Well, what comes next? 96, 97, 98, 99. Again, we don't have to increment yet because we still have the letters to work with. 9A, 9B, 9C, 9D, 9E, 9F. Now we need to increment because F is the highest. So what comes after 9? Remember, A, and then this one becomes 0. So that, isn't that interesting? You go from 9F to A0. That's doesn't look right, but that's how it works because after 9 is A, after F resets to 0. A1, A2. Now let's say we get all the way to F9, and we continue on FA, FB, FC, FD, FE, FF. Now we're full. Both characters are at the maximum that we can allow. So that means, so all F's means that we have to continue on to a new digit, 100. That's the next one, then 101 and so forth. So that's how hexadecimal works. But I want to show something interesting. I'm going to use the hex function, or the, let's see, hex to decimal. See, I'd like to know what this is in decimal, please. And you see, Excel tells me this FF is the same, and hex is the same thing as 255 in decimal. So that means we can count as high as 255 with just 2 places if we use the hex system. Now, why in the world did I bring up hex if binary is what computers speak? Well, the reason why is because in computer programming, you often work with what's called a byte. And we know, you know, if you buy a phone, like an Android phone or something, you can usually get a 16 gigabyte version or a 32 gigabyte and megabytes and all that stuff. But everything, computers and storage, hard drives and whatever, tend to work with bytes. Instead of just 1 digit at a time in binary, we use 8 digits. So I'm going to say, or 8 bits is sometimes what they say, 8 bits. So here's an example of 1 byte. I'm going to put 1, 2, 3, 4, 1, 2, 3, 4. Uh-oh, Excel optimized that. I'm going to have to, oops, tell it not to remove leading zeros by telling it it's text instead of a number. Now if I type it in, 1, 2, 3, 4, 1, 2, 3, 4. There's a byte. That's because it's 8 bits. And so a byte is 8 binary bits. So it can be, each bit can be a 1 or a 0. Well, this would be the equivalent of 0 decimal. But we can continue on. 1, 2, 3, 4, 1, 2, 3. So that byte is the number 1 in decimal. And of course we can continue on counting binary. So we're counting the same way, except we just have these leading zeros in front of us. And before, all the leading zeros to the left in binary were just sort of gotten rid of. We didn't bother keeping track of them. But with a byte, you keep track of 8 characters smushed together, and then you can keep going. At some point, you will fill up 1, 2, 3, 4, 1, 2. Let's just say we're at that. We can continue on. Next number would be that. Oop. There. So now I've counted as high as I can with 8 bits. All 8 have now been filled up to the number 1. Let's see if, let's see, binary to decimal. I'll make Excel convert it for me. So this number here, this byte, is the number 252 in decimal. And we go all the way up to 255. So here's what I wanted to point out. If you're working with a byte can only count from all zeros to all ones. And that is the same thing as 0 to 255. So 0 to 255. You know, and I'm going to move these down just a bit. Well, what if I had, so if you want to count any more than 255 in a computer, then you have to use something bigger than a byte. So the next thing you can do is 2 bytes, which is the same thing as 16 bits. And Excel actually, so it looks like this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Oh, and Excel optimized it again. Darn it, I'm going to click on this then, format the whole column to be text, and now it should do that. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There, that's a 16-bit number, which is 0. And it can go all the way up to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that would be, Excel won't, that's too big for Excel to convert for whatever reason, but that's another way to do it is 2 to the 16th. That is how big 2 bytes together can count, 65,000. All right. So we're going to see when in programming we're going to be making decisions about when we'll be making something called variables, which is basically a temporary place to store a number. So if you want to store a number that's always going to be between 0 and 255, then you can make a variable that's 8 bits big or long, and that'll be fine. And so the processor will only have to keep track of 1 byte. However, if you want to go from, if it's going to be bigger than 255, then you need to go up to the next size, which would be 0 to 65,000. So it's just something to keep in mind, and we'll go into this more in programming, but I want you to understand where this comes from. It comes from the idea of bytes and counting in binary, and all zeros gives you 0, all ones for a 16-bit number gives you 65,000. And by the way, you might have heard about processors being 32-bit or 64-bit. That has to do with or 8-bit even. In fact, the AVR processor that we'll be working with in the Arduino is an 8-bit processor. So that just has to do with how big the little pieces of how big the numbers are that it's used to working with natively, and how big they are. So finally, why did I bring up hex? The reason why is because, let's continue, let's bring this number here. I'm going to copy this number down here. You can think of that as two pairs of, or it's 8 digits long, but if we thought of them as two different pieces, 1, 2, 3, the first 4 digits, and then the second 4 digits. So I took the first half, put it here. I took the second half of this number, put it here. So I broke it up into 2 pieces. Well, this 1111 is is F if we do hex, and then 1101 is D. So what we can actually say is, I'm going to copy, well actually I'll just use this. This number in binary is the same thing as FD in hex. So we can represent 8 digits of binary with 2 digits of hex. So it's a shortcut that you often will see. We're not going to be using hex too much in programming that I can think of right now. Usually we think of in binary terms for some purposes we'll get to, but I just wanted you to know that hexadecimal is a way to shorthand represent a binary number with fewer digits, and it just happens to work out perfectly that if you cut a byte in half, then the first half will never be bigger than F, and the second half will never be bigger than F. So we can always use one of the hexadecimal characters to represent either half of the byte. So that means that a byte can be everything from 00 hex or all the way up to FF in hex. Okay. All right, well that's enough. I don't want to get too far into this. Main takeaway here is that computers use base 2. This is how you count in base 2. And I also want you to know that a byte is 8 bits, which can go from 0 to 255. So all zeros, which is here, all the way to all ones, which is here. So all zeros and all ones is the same thing as 0 or 255. So that's why you have that limit. And then 16 bits is it's going to be quite a bit more, 0 to 65,536. All right, so we'll do some worksheets or something in the class, and we'll go over it a little bit more. But this should be enough for now. Thanks.